Okay, notes for 5.2, verifying trigonometric identities. So this is the section where we're going to do trig proofs, like everyone's heard about. So verifying trigonometric identities. The first thing we're going to do before we get into the examples is talk about what it is to verify a trig identity, how to do it, and give you some hints as to the methods that are going to help you get to the proof itself and to verify. So here we go. Verifying trig identities. To verify means that you want to prove both sides of the equation are equal. That's essentially it. And that has to be true for all values of the variable for which both sides are defined. And here's how we're going to do it. We're going to transform one side of the equation into the other side using identities. So, and remember, as with other types of proofs, each step is justified with a reason. Now that doesn't mean we're going to write it out, but the reasons are using those proofs that we know to be true. We proved them yesterday or in the notes for 5.1, so we know them to be true. Okay, so as a hint, this is what we're going to do, I would say 99% of the time, but it is usually easier to start verification of a trig identity by beginning on the side with the more complicated expression I'm just going to warn you now, there is not enough room for me, so I'm going to have to double up on some lines. And working toward the less complicated expression. So basically, when you look at these equations, you're going to decide which side, left or right, you think looks more complicated. And then start with that side and try to work it down using identities to eventually get to the other side, meaning you want it to look exactly like the other side. There will be some where it's kind of a toss-up. Half of you may think the left side looks easier, whereas the other half thinks the right side looks easier. It still will work out. It just depends on the trig identities that you're going to use, but it doesn't always. Sometimes there are cases where you really could choose the left or the right. They both kind of look the same. Okay, so methods for verifying trig identities. These next few bullet points are going to be some hints to get you started, some things to be looking for, and as you start to practice these, you're going to recognize them and kind of learn the ropes, learn how to think through these. Okay, so the first one will be to use reciprocal, identity, Pythagorean, quotient, and other basic identities. So when you do these, guys, you really want to have those identities out right next to you where you can look at them very quickly. Okay? All right. You're going to use algebraic operations. There's actually a lot of algebra techniques used in proofs. So use algebraic techniques. Such as combining fractions, rewriting fractions as sums or differences, which is where we're going to break them apart, multiplying expressions, or factoring expressions. So lots of algebra with some of these, with a lot of these actually. Okay, another technique that you may use would be to convert a denominator of the form. So again, this is where we might use the conjugate. If we have the form, 1 plus or minus u, or u plus or minus 1 to a single term, using its conjugate, and then possibly a Pythagorean identity. So these are all going to make a little more sense after we do a few, and you can go back and kind of look at these ideas and say, oh yeah, okay, I've used that, and you know, it's kind of tough to wrap your head around until you've done some. This next one I'm going to list. We don't do it very often, but it can be done, so I'm going to list it. You can work each side separately to reach a common intermediate expression. So in other words, instead of trying to find the side that's more complicated, you kind of try to work both sides down and meet somewhere in the middle when you get them both equal. I'm going to be honest, that's not how I'm going to show you to do a lot of these. It tends to just be easier to focus on one side and manipulate it using the identities into the other side. Okay? And last but not least, if no other strategy works, try converting, and I shouldn't say works, let's erase that. No other strategy, let's say this, comes to mind. Okay, so if you can't think of anything else, I would try converting the entire expression to involving only sine and cosine. There's a lot of ways that those relate. So a lot of times, if nothing else is jumping out at you, try to put everything in terms of sine and cosine. And just get ready, guys. You are going to try some things on these homework, maybe not have anywhere to start. You just have to jump in. You just have to try something. It just comes with practice. There's no, first do this, then do this, then do this. You're just going to have to start looking at these identities, working with them, substituting in, and practice to kind of get the hang of it. And there will be a lot of things that you see repeating, but you're never going to familiarize yourself with these if you don't practice them. So let's get started. All right, example 1 says to verify that the cosecant squared of x minus 1 equals the cosine squared of x, or over cos squared. Cosecant squared of x minus 1 over the cosecant squared of x equals cos squared of x. So I'm going to say that definitely the left side looks more complicated. So I'm going to work on the left, and my goal, my end game, is to have cosine squared of x on the left. So I want to use some trig identities They are saying right now, they're not asking me if this is true. They are saying that the left equals the right. And it's my job to prove it through these identities. It's not a question of if it's true. It is definitely true, and we need to get to show how. Okay, so as I look on the left, I see cosecant squared x minus 1. So guys, when you start seeing things squared, that should start jumping at you. You start scanning through those Pythagorean identities. And if you scan through the Pythagorean identities, you are going to see one of our manipulations is that the cosecant squared of theta minus 1 is the same as cotangent squared of theta. If you are not looking at those identities, you should be flipping back. The cosecant squared of theta minus 1 is equal to the cotangent squared of theta. So I'm going to start by substituting cosecant squared theta for cotangent squared of x, and that is over cosecant squared x. Okay, so I'm working my way down the left side. Okay, so what I have now is cotangent squared over cosecant squared. That is division, so I'm going to break that up. We know that cosecant squared is really cosine squared of x over sine squared of x. I am dividing that by cosecant squared, which is really 1 over sine squared of x. Now, if you don't see that the sine squareds cancel this way, let's do this. Let's rewrite it even further. Spread this division out horizontally, and we can say that the cosine squared of x over the sine squared of x is multiplied by the reciprocal of 1 over sine squared, which is sine squared x over 1. And now hopefully you see that the sine squareds cancel, and I am left with cosine squared x, and that is what I needed. Cos squared x equals cos squared x. So there is your first identity, okay? So we worked the left side to get it to equal the right side, looking at those identities and trying to figure out some equalities that we can substitute in. Okay, let's try example number 2. This is a true statement. 2 times the cosecant, that should be cosecant of x, is equal to 1 over the cosecant x plus cotan x plus 1 over the cosecant x minus cotangent of x. So I would definitely say that the right side is more complicated. So we are going to start to manipulate the right side so that at the end we get it equal to 2 times the cosecant of x. So I have 2 fractions with different denominators. Hopefully you're thinking, let's get a common denominator. So I'm going to take and multiply. They are conjugates of each other, so I'm going to multiply those conjugates. So on the 1 over cosecant of x plus cotan of x, it's going to be hard to squeeze it in here, but it's going to be cosecant of x minus cotan of x on the top and the bottom. So I'm going to multiply by cosecant of x plus cotangent of x on the top. And over here, I'm going to multiply, whoops. Ooh, sorry guys. I just want that to erase just a little bit there. That's minus, okay? On the other side, it's going to be cosecant of x plus cotangent of x, the conjugate, and I'm going to also multiply it to the top. Sometimes these can be tedious. Just hang in there, ignore it, and just push through that. Okay, so now in the top, 1 times both of these things leaves me with cosecant of x minus cotangent of x plus the cosecant of x plus the cotangent of x. I don't need parentheses because it's plus. I don't need to distribute a negative. That is going to be over cosecant of x minus cotan of x times the cosecant of x plus cotan of x. Those are conjugates. So all I have to worry about doing is the first and the last, and I get cosecant squared of x minus cotangent squared of x. Okay, if I look at the top, hopefully you see that negative cotangent of x plus cotangent of x is gone. And in the top, I get 2 cosecant of x. Oh my gosh, that's actually what I need on the left. But what about cosecant squared of x minus cotangent squared of x? We are going to go to our Pythagorean identities. You are going to look back and look for things that have cosecant squared, cotangent squared. That's in your Pythagorean identities, and you should see it. It is one of the last ones. Cosecant squared minus cotangent squared is equal to 1. So I get 2 cosecant squared of x over 1, which is 2 cosecant squared, or 2 cosecant of x, and that's exactly what I needed, 2 cosecant of x. Just takes practice. This was using the conjugate to try to work something, to try to get to one of these identities and make some substitutions. Okay, let's look at the next one. Okay, this is one where some of you may say the left side looks more complicated, and some of you may say the right side looks more complicated. And you can try to do it where one of you does it one way and the other does it another way, or you can try both ways, because this one really doesn't matter. I actually chose the left side to work with. Maybe it's the fraction that I see that makes me think it's more complicated. So I'm going to work with the left side. I have the sine of alpha over 1 minus cosine of alpha. And I need to get that to equal the cosecant of alpha plus the cotangent of alpha. So what I'm going to do, again, I see 1 minus cosine of alpha. And you're going to see, hopefully quickly, when I start to use those conjugates, that they run into and turn into Pythagorean identities that I can use. So I'm going to take and multiply the top and the bottom by 1 plus cosine of alpha. 1 plus cosine of alpha. So in the denominator, I have 1 minus cos squared of alpha because they are conjugates. Now in the top, you could distribute, and when you're doing these at home for your homework, you might do that and then realize, wait, I shouldn't have distributed. I am going to leave it as 1 plus cosine of alpha times the sine of alpha. So as I look at this, here's why. You start to see these things looking ahead. 1 minus cosine squared. Go to your Pythagorean identities. You have a cosine squared and a 1 being added or subtracted. You want to go look at your Pythagorean identities, and sine squared plus cos squared is 1. So you also have that 1 minus cos squared is equal to sine squared. So we're going to change this denominator to sine squared. Well, I have a sine of alpha in the top. Oops, that's supposed to be an alpha. And I have a sine squared in the bottom. So what happens is the sine in the top cancels with one of the sines in the bottom. And I end up with 1 plus cos alpha over the sine of alpha. Okay, now I needed to become cosecant of alpha plus cotangent of alpha, and there's no fractions there. So what I'm going to do is I'm going to split up the left side. It's totally legitimate for me to say 1 over the sine of alpha plus the cosine of alpha over the sine of alpha. The sine of alpha was my common denominator, so I just split them up. Now, as I look at these identities, I know that 1 over the sine of alpha is the same as cosecant, plus cosine over sine is cotangent. And so now we have cosecant of alpha plus cotangent of alpha on both sides. Check, check. All right. Okay, let's do example number 4. Yikes. I hope you're agreeing with me that the left side is definitely the more complicated side. This is really long. This whole thing is equal to the cosecant of theta. So as I look at the cosecant of theta, I know that that is actually 1 over the sine of theta. So in the back of my mind, I'm thinking, all right, I want to get to sine and cosine because eventually that's what I need. So there's a lot of these are reciprocal functions, cotangent, secant, cosecant. So I actually split them up. I just want to end up with 1 over sine theta or cosecant. So I'm going to split this up. Cotangent is really cosine of theta over sine theta. Secant is 1 over cosine theta. Cosecant squared is 1 over sine squared theta. Minus cotangent cubed is cosine cubed theta over sine cubed theta. Then I have the secant of theta, which is 1 over cosine of theta. Okay, so now I'm going to start canceling some things out. On the left, love this part, cosine cancels with cosine. I'm left with 1 over sine cubed of theta minus, over here, cosine cancels with 1 cosine in the numerator, leaving me with cos squared theta over sine cubed theta. Well, lucky me, we have a common denominator, so I can put those together. 1 minus cos squared theta over sine cubed. And I don't want to split these back up because I just put them together. So now I'm looking at my Pythagorean identities. Sine squared plus cos squared is 1, and the manipulation of that, 1 minus cos squared is sine squared. So I'm going to exchange 1 minus cos squared with a sine squared. So I now have sine squared theta over sine cubed theta. And both of those signs cancel with one of those, and I have 1 over sine of theta, which is equal to cosecant of theta, and that's exactly what I needed. Okay, just wait till you get going on these. They're a lot of fun. You'll love them, trust me. Okay, we have one more. That might take a while for you to absolutely love them, but they do, the quicker you guys study those identities and get comfortable with recognizing them, the easier it's going to be, but that does take some time. All right, example 5. Again, this is another one where you look at the left, you look at the right, and one of you might say that the left looks more complicated and the other one says, no, I'm going to take care of the right. I actually picked the right or the left-hand side, tan squared over 1 plus the secant squared. So I'm going to try to get that all in terms of cosine. So I'm going to work this left side down and try to get it in terms of cosine. Well, I know that secant is the reciprocal for cosine. And if I look at tan squared, always when you have something squared, go to those Pythagorean identities. When you look at tan squared, that is the same as secant squared. Tan squared is equal to secant squared minus 1. So I'm going to replace that. Secant squared of x, minus 1 over 1 plus secant of x. Well, secant squared of x minus 1 is the difference of two squares. So I know that that is the secant of x minus 1 and the secant of x plus 1 over 1 plus the secant of x. And hopefully you're seeing that these are going to cancel. The secant of x plus 1 is going to cancel. And so I am left with the secant of x. Great. The secant of x minus 1 is going to equal, I still don't have it in terms of cosine, so I'm actually going to write the secant as 1 over the cosine of x minus 1. Well, if I want to combine these, because remember, I'm trying to get it equal to 1 minus cos x over cos x, so I'm actually going to get a common denominator. So I'm going to turn 1 into the cosine of x over the cosine of x. And now when I combine them, I have 1 minus the cosine of x over the cosine of x. And I have my proof. Okay. So those are about 5 examples on how to do these trig proofs and verify these identities. And like I said, we can't hit every single one that you're going to see. All we can do is give you those identities, give you some techniques that you can practice with, and you are going to get better at this with practice, I promise. So good luck. Thanks, guys. Have fun.